Good morning, honorable speakers, distinguished guests, ladies and gentlemen. Welcome to the seminar series of International Seminar on Chemical Engineering Suhardi Reksawardoyo, known as STKSR, in conjunction with Symposium on Photocatalysis and Photocatalysis, known as Symphosis, with the theme of Industrial Water Use, Innovations and Practical Applications. I'm Faturu Wisono, student from Department of Chemical Engineering, Institut Teknologi Bandung. It is a great and valuable chance for me to be a master of ceremony in today's event. On behalf of 2020 STKSR Symphosis Committee, I would like to extend a very warm welcome to all of you. We appreciate taking time of your busy schedules to join us today. This webinar series is a type This webinar is a series of pre-events from the 2020 STKSR Symphosis activity organized by the Department of Chemical Engineering, Faculty of Industrial Technology, Institut Teknologi Bandung, with the theme of Circular Economy for a Better World. The 2020 STKSR Symphosis series is supported by the ITB Chemical Engineering Alumni Association, Badan Kejuruan Kimia Persatuan Insinyur Indonesia, and the ITB Chemical Engineering Student Association. I would like to start this event with the national anthem, Raya. Ladies and gentlemen, please rise. Ladies and gentlemen, please be seated. Next, I will convey the health and safety regulations in these pandemic conditions. If you're outside the house, then 1. Participants must use masks and other personal protective equipment. 2. Participants must keep a distance of at least 1 meter from other people. Then, I will read the rules of conduct during the event. 1. Participants are not allowed to turn on the mic and camera during the event. 2. Participants are only allowed to ask questions through the chat room in Zoom or YouTube from the beginning of material presentation by speakers until the end of question and answer session. 3. Participants are mandatory to fill in attendance form correctly through the link that will be provided in the chat room in Zoom or YouTube during the webinar. The data will be used to send e-certificates for the purposes of sending for those who previously registered. Now we are pleased to have an opening speech from Mr. Professor Dr. E. Gedewanten, the Vice Rector for Research and Innovation, Institut Teknologi Bandung. He is a professor in membrane technology and also a lecturer from the Department of Chemical Engineering, Institut Teknologi Bandung. Professor Wenten, the time is yours.
Good morning, everybody. Can you hear me?
Yes, clearly.
Yes?
Yes.
Okay. Yes, thank you. Excuse me, I need to switch off my video to have a better connection. Yeah. Good morning, Professor Kazuo Yamamoto, Professor Hiroshi Yamamura, Dr. Kazuhisa Mimura, Mr. Toru Nakano, Prof. Chandra Tiadi. Hello, can you still hear me? Hello. Hello, can you still hear me?
Yes.
Okay. Yes, good morning, Prof. Kazuo Yamamoto, Prof. Hiroshi Yamamura, Prof. Kazuhisa Mimura, Prof. Toru Nakano, Prof. Chandra Stiadi, all respected participants, ladies and gentlemen. It is a great honor for me, on behalf of Institut Teknologi Bandung, to welcome you.
Suaranya harus. I think so.
Participation and your support, and we extend our best wishes successful and fruitful. This year, the theme of STKSR Circular Economy for a Better World, while the topic of today's seminar is innovation in practical application in industrial water reuse. As we all understand, the circular economy is an economic system of closed loop in which the raw materials, components, and products are utilized sustainably with the ultimate goals to eliminate the release of waste, pollution, and carbon emission, as well as the continual use of resources. Circular system include action of reducing, sharing, repairing, and manufacturing and recycling in order to achieve its goal. Ladies and gentlemen, as we all know, that water is indispensable in all industries, as in the life of all living beings. Therefore, industrial water use, which is the topic of this webinar, must be included as part of the circular economy. Innovation and practical application of water processing and reuse in industry should be encouraged and disseminated. This is the purpose of this webinar. It is recognized that the research, studies, and innovation in the field of industrial water use have been widely explored and implemented and have exhibited a substantial role in shaping the circular economy. Therefore, it is of significant importance to facilitate knowledge sharing and brainstorming sessions among scientists, industries, and all stakeholders in this field. I believe that this exciting webinar to be held today will promote the advancement of the industrial water use as part of the circular economy. On this occasion, I would like to express my sincere gratitude to all invited speakers, honorable guests, and all respected participants in this wonderful event today. Moreover, please allow me to congratulate and to thank the committees, which have put their excellent works into organizing this webinar. Finally, I wish that this event will be a wonderful opportunity for us to exchange ideas, broaden our horizons, and nourish collaborations between the related fields. In the future, we shall continue to work closely together to promote the development of science and technology. Once again, please allow me to wish you an enjoyable, successful, and fruitful webinar. Thank you.
Okay, thank you, Professor Wenton, for that wonderful speech. Now, continuing the following agenda, we are pleased to have an opening remark from Professor Insinyur Chandra Stiadi, PhD, the head of the Center for Environmental Studies, Institut Teknologi Bandung. He is a professor of bioprocess technology and environmental policy and also a lecturer from the Department of Chemical Engineering, Institut Teknologi Bandung. Professor Chandra, the time is yours.
Thank you, Father. Good morning, everybody. So I think so. Professor Benton is already give in the speech in his speech, but I think I just briefly what is the relation between the our seminar in November and then with this current webinar. So of course, I would like to address first to Professor Yamamoto, my colleagues, we have a collaboration with Professor Yamamoto more than I think 10 years, and then also to the others colleges, also to Professor Benton and also Professor Yamamura, and the other speaker, Dr. Mimura, Mr. Nakano, and also to the moderator of the webinar, Dr. Helen. And things the seminar itself will be on the 16th and 17th of November with the theme of the circular economy for a better world. And we already conduct the webinar series number 1, that the title be the circular economy and the sustainable consumption of production. That one was held on the 28th of July. Then today we will discuss on the industrial water reuse. So that one is the relation between our seminar in November with the other webinar. So Professor Wenton already mentioned about the goal of the circular economy. Of course, we have to try to generate zero waste. We are living as a human sphere, where the goal of so we have a 17 as the goal in the SDGs, and we are living in the biosphere and also with the technosphere. So how to achieve the sustainable goal, we can do that by generating the zero waste. So that one what we are trying to do, that we produce the product with the processes in the system, and then we use the circular economy to achieve the goal of the 17 Sustainable Development Goal. We understand that in each action plan, we need to do something with the technology. So the value of the products, material, and resources should be maintained in the economy as long as possible. and we have to generate the waste as a minimum as possible. So that one is our today discussion, and we have to bring economy, social, and environmental gain. So I think that one is just give you this summary of what is the relation between the seminar on November and our current webinar. So I think we would like to thank you again to Professor Yamamoto, to the Professor Gedeventon, and also Professor Yamamura, and also Mr. Nakano from Organo, and also Dr. Mimura from Sanki. So I think the colleges from Organo Indonesia hopefully also join the program, and also hopefully Professor Yamamura already joined as well. I think you call it from ITV, Dr. Herto willing to also to say hello to you. So I think we you please have a nice webinar, and thank you to all of you, and then we try to proceed to the main webinar. Thank you very much.
Thank you, Professor Chandra, for that wonderful remarks. Now, I will introduce the profile of today's webinar's moderator. This webinar series will be moderated by Mrs. Helen Julian, PhD. Mrs. Helen is a membrane distillation and desalination researcher and also a lecturer from the Department of Chemical Engineering, Institut Teknologi Bandung. Now, without any further ado, I would like to invite Mrs. Helen to begin the main session of this event. Mrs. Helen, the time is yours.
Okay, thank you, Fatur, for the nice introduction. So, first of all, please allow me to say good morning to our invited speakers from Japan and Indonesia, and also good morning, ladies and gentlemen. Today's webinar will be divided into two sections with 5 distinguished speakers. In the first session, we will have Dr. Kazuo Yamamoto, Professor Igede Wenton, and Professor Hiroshi Yamamura to deliver the lecture on the industrial water reuse. Our first speaker is Dr. Kazuo Yamamoto. Dr. Kazuo Yamamoto is the president of Water Reuse Promotion Center in Japan. Membrane bioreactor development is his major research contribution, by which Professor Yamamoto got various awards such as Sydney Awards, Membrane Technology Award, Academic Awards, and others. Our second speaker is Professor Igede Wenton. Professor Igede Wenton is the professor in membrane technology in ITB. He currently serves as the Vice Rector for Research and Innovation in ITB. Professor Wenton is the leading researcher on membrane technology in Indonesia, with numerous patents and has received various awards for his breakthrough research activities. And our third speaker, the last speaker for the first session, is Professor Hiroshi Yamamura. Professor Hiroshi Yamamura is the professor in Environmental and Separation Engineering with specialization in membrane filtration and solid liquid separation process. Over the past 8 years, Professor Yamamura has been engaged in various research and application of membrane processes. Currently, Professor Yamamura is engaged in research on the construction of a smart water infrastructure using big data obtained from waterworks. Okay, to begin with, to start session 1, let us welcome Professor Yamamoto to deliver the first lecture. Professor Yamamoto, please, the time is yours.
Morning. Thank you very much for the kind introduction. And thank you for inviting me, thank you, Professor Chandra, inviting me to this conference. So I will present today as a president of the Water Reuse Promotion Center Japan. And I have been engaged at university a long time, the University of Tokyo, but I retired already. And then, this today, the focus is the circular economy, and then, just a moment. So either to share my slide, just a moment. I need to search. Sorry, I can't the shared file. I can find.
I think you have to open the file first in the your presentation.
Yeah.
It's better to open first before. Okay. Great. So
Okay, thank you very much. Thank you for introduction. So I let's start this presentation activities for industrial water use, rationalization of water use. And then, yeah.
So Yamamoto, you can make a few slide view to make a better presentation of yours.
Yeah.
Okay, thank you.
All right.
Yes.
Okay,
All right.
thank you. Sorry, I have to used to be this one. Okay, so
great.
Anyhow, I had to start this slides as a representative of the Water Reuse Promotion Center Japan. And this activities of industrial water use. Industrial water is very much important part of the water usage in the world. And then rationalization and water reuse is very much important in industry. And this is very much contribute to the circular economy as well. And then our center, Water Reuse Promotion Center, has been developed, has been established in 1973. And then this is independent, non-profitable organization supported by METI, but it was transferred into the General Incorporated Foundation in 2010. And then this center, I'd like to briefly introduce the composition of this center, the members, and 28 local governments, 7 major industrial water consumers, and 36 water processing equipment industry and engineering companies. And then our center has objective to develop and disseminate water treatment technology in order to solve the problem of water shortage and water pollution. And activities are summarized below, and I will show you later. And then also, in addition to the R&D, and our mission is provide consultation of the water use rationalization in industry, and also technology transfer of the possible technologies, promising technology to the world. Water Reuse Promotion Center. This is our English translation, but the direct translation, direct pronunciation of our center is ZOSI Promotion Center. ZOSI means water creation. Water creation. So, sorry. This means ZOSI is not necessarily water reuse, and this is a wider concept. But however, this is Japanese terminology, so we use Water Reuse Promotion Center as English name of our center. ZOSI is a water creation. And then water generation, of course, from possibly from air, sea, ground, and river, lake, and others. And the seawater desalination is now practically applied in the world, and water reuse. And it's very much important to cascade use and reclamation. And also, effective use is our mission. Less or minimum consumption. This is very much related to the circular economy in the industry. Then Zosi Promotion Center focusing on these technologies: desalination, wastewater reclamation and its reuse, and effective use of water saving in various industries. This is our mission. Everyone recognize, anyhow, this is a statistical data of the rapid growth of the population, and then water intake is more than that in the last century. And also, if you're talking about the water demand in the world, so of course, irrigation purpose is the largest one, and domestic one, but manufacturing also is not negligible. And then it is projected in the 2050. This project is a manufacturing purpose is rapidly expanded. So it is becoming more important to utilize new or unconventional water source. It is possibly sewage, wastewater, seawater, used water, and so on. By applying this kind of water reuse, we call it Zosi technology. And then this is the energy consumption. Example of the energy consumption is reported by this organization. And then, of course, still it is challenging. If we're talking about water reuse technology, still there's a wide range of the energy consumption, but and the seawater desalination also, but it is improving. It is improving a lot. And then this energy reduction is successfully done recent years. So then there's a much room of the application of the water reuse in the various field. And then this is a summary of the world percentage of the water reuse by application. Then, of course, agricultural purpose is the largest one, but industrial purpose is not significant. This is also the large part of the reused water is utilized in industry. If we're talking about Japan, so this is total intake of the water, and then this is agriculture purpose, of course, the largest, domestic, and industry. And then this is amount is not changed so much. In 1960s, industrial water demand is expanded a lot. But at the same time, because of the shortage of the freshwater resources, in late 1960 and 70s, in Japan, there was tremendous work on the recovered water application. Then it was successfully done. Then you can see this is the recovery ratio percentage. In the average, it's almost 80%. And then recent trend is the total amount of the water used is also decreasing. This is also partly due to technology innovation, which consume less water, or effective use of water, promotion of the effective use of water, water minimization, like that. Of course, water demand, water intake varies a lot from industry to industry. variety of the water consumption happens in various industries. Top 3 is chemical, steel, pulp and paper. But largest one, chemical industry or steel industry, is something like good, shows a very good performance in terms of the water recovery, much more than 80%. But pulp and paper, less than half. Food and beverage, very small. So this is a variety of the water usage happens in a variety of the industries. And then it's very much important to improve water consumption in the food and beverage still. Here, this is a graph for the water recovery, higher water in recovery industries, and a lower one. And then food and beverage one. This one is a composition of the water usage, industrial water supply, municipal water supply, well, groundwater, and others. And the recovered one is this portion. So it's very important to conduct effective use of water. And then most important piece of this one is enlightenment or education of the people or stakeholder to save in mind or manage its management is very important. This is the base. But in a technology-wise, cascade use of wastewater is very much important. Then recycling water, such as cooling tower water, and recycling for inside factory. And then also water saving technologies can be adopted in each facilities, in each factory industry. So like this, water supply is here, and we'd like to know, maximize the way of cascade use and recycling, then minimize the water discharge, wastewater discharge, and this is going to the treatment processes. Then our center targeted more than 2,000 cases in Japan, and this kind of our center has experience of the successful application of the rationalization of the water use for industry. Cases more than 2,000. And then the result is successfully saved around 23%. So this is a before and after the beverage factory. Before and after of the example of the beverage factory. So before this example, before clean water is 4,300 cubic meter per day. This is a water supply. Tap water is municipal water supply, and then tap water supply, and then groundwater. Then this is going to the every processing, but the rinsing process, this is use centrifugation, and then this going to wastewater treatment. Cooling process, heating process, pasteurization, and then cleaning process. This is going to wastewater treatment. Only this line is recycle. After improvement, water intake is reduced a lot. Wastewater amount is reduced a lot because This is a technology innovation, a kind of the technology application, floating type. And only this part is going to wastewater treatment. Most of them are recycled. And then cooling tower, also this is used, this one is used to cleaning process. This is a successful example of the cascade use of water. And also pasteurization. This is filtration, the nanofiltration is applied. And then this is also cascade use to cooling tower. Because of this cascade use of water or recycling, effective recycling of water, amount of wastewater discharge is reduced a lot. Also, water intake, freshwater intake reduces a lot. So this is an example. This is example. Then R&D, if you're talking about R&D, and then R&D in terms of the water use, this is related to the circular economy also. And then now we need energy or valuable material recovery also, as well as water use reduction, reduction in the water, reduction of the water consumption. And then typical technology in the practical application. And this is just example. Our center tried to USB MBR in Thailand as a pilot plant. And also anaerobic MBR, which energy recovery is now either introduced by this presentation. So probably Professor Yamamura mentioned about the channel membrane technologies, and then the low energy labor, low intensive labor requirement treatment process of the biological treatment or variable material recovery, utilizing the advanced membrane system, RO system, for electric industry and so on. So in Thailand, 2001 to 2005, our center set this pilot plant as this is a biological treatment USB anaerobic approach large blanket process, and then this is food processing factory, and part of them is try to utilize MBR so much, MBR and RO for their use. Anaerobic MBR is it's a long history, and then it started from 1978, and in 1980s, late 1980s, Japanese initiative of national project called Aqua Renaissance 90s. This aims to develop high-performance anaerobic bioreactor with high efficiency membrane separation. So this national project not yet realized in a practical use as it was as a whole system. However, membrane unit process or membrane materials or membrane module has been developed a lot by this project, R&D project, low energy membrane module for high concentration sustained solid, and so on. Then this developed membrane technology has been actually utilized a lot in aerobic treatment first, municipal wastewater treatment and industrial wastewater treatment, disseminated a lot in the world. Part of them is MBR, membrane bioreactor. Then this kind of the practical application or increase in the market of the membrane application will push another stage of anaerobic membrane bioreactor development. This is very important. R&D, of course, for example, R&D in Aqua Renaissance was not successful in strict sense, but this gives a lot of development of the membrane technologies. And this gives a application field. This expands the market of the membrane application in water use or wastewater reclamation. Then this again push membrane anaerobic treatment, anaerobic membrane application. Then now in Europe, especially in Europe, the case in Netherlands, chocolate factory wastewater 500 cubic meter per day, or several plants has been applied practically in an anaerobic membrane, but as an anaerobic membrane bioreactors. Now it is expanding. So of course it takes time, but this kind of innovation is not R&D only. Innovation means dissemination of technology in the world or some regions. So this is a case of the example of the innovation of the membrane application. And then I'd like to mention again about the ISO scheme, and our center is involved. Of course, if you're talking about the innovation or dissemination of technology, we need then if application is of course first and disseminated, and then we need standardization in order to make common some technological guidelines of that technologies. And then water reuse also. Now we are this stage, and then we need some standardization of the water reuse technologies. These tables, technical committee tables, summarize various technology, and then seawater desalination is here, and the water reuse here. And then we have a subcommittee.
Excuse me, Professor Yamamoto, the time is 2 minutes left.
Okay, thank you.
Thank you.
I will finish soon. And our center is here, this subcommittee, and then our center is involved of this subcommittee, and then this is risk and performance evaluation of technologies. And then this kind of new technology or innovative technology are listed for this evaluation. And then if you are interested in this, and Mr. Nakamura in our center will discuss in details. Thank you very much for your attention.
Thank you, Professor Yamamoto, for a very insightful presentation. Okay, thank you, Professor Yamamoto. Now let's continue to our next speaker, Professor Igede Wenten, who will explain about the Indonesian perspective on industrial water reuse with membrane. Please, Professor Wenten, the time is yours.
Thank you. I'm sorry, I'm using two connections, one with computer and one with my mobile phone, because I think I have problem with my computer speakers. Can you see my share screen?
Not yet, Prof.
No?
Not yet. Okay.
Not yet? It's okay now?
It's okay now. It's okay now.
Oh. Okay, good morning, everybody. Can you hear me?
Yes, clearly.
Yeah, I supposed to talk about membrane bioreactor, but anyway, last night I discussed it with Professor Chandra that so many talk already in membrane bioreactor in this series of webinar. So I just changed my topic, so industrial water use membranes in the Indonesian perspective. So before we come to the main topic, I would like to introduce you a little bit of what we had done in Indonesia regarding membrane technology application. So this is a patent that I have registered in the Indonesian Patent Office and also abroad, like United States patent when I did my PhD long time ago in Europe. So this is the application, and this was commercialized by Explo, and I was joining Explo around 30 years ago, commercializing this technology. This is something to do with the use of micropenetration for produce clarifications, and also for beer clarification, biotechnology clarification, etc. And back to Indonesia, I developed this technology, what we call as a conductive electrodialysis technology, known later as a electrodeionization, and the commercialization of this technology is just started maybe 5 years ago. And then we also developed this kind of application, and this is a membrane module for tsunami relief. Just a moment, I would like to make a clear, because in my, I have some notification here in my screen, so I cannot see my slides. Anyway, it's okay. I just go quickly. And also we have this evaporation applications, and we have also some application in cane sugar clarifications. And then this is a ceramic membrane plant for water use in palm oil industry. And this is for physio clarifications. And this is for palm kernel oils. And this is for chatrova. And this is for gelatins. I cannot see my slide, but anyway, this is lube oil clarifications, and this is membrane plant for produce water injections, and we have application pilot scale for membrane contactor for CO2 removal. This is what we call as a web-free membrane contactor, and this is for high cell density microalgae cultivations, and this is for just a moment. How can I go with this? Right? Yes, okay, I just go quickly, and this is for oil extraction in palm oil industry. So we are showing super hydrophobic membrane here, and this is for coconut water clarification, and this is for palm sugar concentrations. And here is a low glycemic index cane sugar. And we also developed this kind of technology. This is a combination of 4 different technologies. That is a membrane equipped with ZNO nanoparticles for antibacterials and activated carbon, and also bioceramic and single module. And this is a very compact, and we use it for home water filter applications. And the same technology we use it for emergency filter, and this is the smallest version of this technology. And we also developed this kind of technology for household using the same technology. But this is ultrafiltrance for a little bit bigger capacity, and this is for home industry. And here is a molecular air filter, and we developed this 5 years ago for this removing all aerosols from burning of forest 5 years ago. And in fact, this was developed further in a large scale, and this was actually the plan we make in December 2019. And this large scale air filter, molecular air filter, can eliminate almost 100% aerosol, and now it's used for COVID-19 virus removals. And then this is what we develop also. This is fiber reinforced plastic for high pressure housings membranes. So those are all, I think. But anyway, when we are talking about industrial water use with membranes, from the Indonesian perspective, we first of all would like to introduce a little bit the role of membrane for zero liquid discharge. And there are 4 steps here, and I have taken this picture from this source. So the first one is pre-treatment, and then biological, and then membranes, and then evaporation. But anyway, in the case where you don't want to have or you don't have this biological treatment, you actually can also go from pre-treatment to membrane directly. In Indonesian perspective, so we have some big application in palm oil industries, and then also in aquaculture. This is a very unique. I think we have many experience in applying large scale membrane for industrial water reuse in aquaculture. Not very large, but anyway, some is actually quite big. Then there's clean production in start industry or other agriculture industry, and also we have a lot of this produced water. This is a waste from oil and gas industry, and also we have experience in reusing water in electroplating, and this is actually a membrane bioreactor that we use for biological treatments, converting some of industrial wastewater to industrial water reuse. And here is the technology that we develop a membrane bioreactor. So this is what we call as an implanted and spray membrane bioreactor. So the membrane is spotted, yeah, and the bottom here, yeah. So just a moment, I would like to change this to laser pointer. Yeah, so the membrane is spotted here, and the other end is free. But then this membrane is buried with a granulated activated carbon, and then air is introduced in the bottom. Yeah. So the granulated activated carbon is fluidized, scoring the membrane or cleaning all the dirt that attach to the membrane, and also becoming the house of the home of microorganisms that can convert all biological substances. And in fact, this granulated activated carbon also absorbing some of small macromolecule like proteins, etc., that are responsible for fouling the membranes. So in fact, this actually has been applied or used for start wastewater treatment, and in fact, the result was very good. This is a normal submerged MBR with the same configuration, and this is implanted MBR also with the same configuration. So the results after, yeah, we use the membrane for a long time. So in submerged MBR, so the membrane fouling or biofilm formation is very thick, while in implanted MBR, so the membrane is still clean after long time running. And then also we have applications in aquaculture system. This is actually for reusing water in what we call as a yeah, it's an aquaculture, it's a hatchery. Yes, we also developed this kind of water use, but this is without biological. So this is a very easy. Actually, what we call this as a IGW green ultrafiltration. This is for decentralized water reclamation system. So we can actually very easily produce 500 liters or half cubic meter of water in hour. You just using these small modules. This is a 6-in module with around 1.2 meters high in membrane. So just by pushing these pedals clockwise, then we have the water. When the membrane is getting dirty, then do it the other way around, and the dirt will come out from this pot. Actually. So it's very easy to use. We also have developed this kind of very small. Yeah, this is for community water reuse. Actually, in some places where water is very difficult to get, or you don't have any water, then you also need to reuse the water. So this small membranes module actually has been commercialized for this type of small scale water reuse. So the most important thing development I want to tell you actually in this talk is something to do with the development of non-modular membranes. So this is yeah, maybe around 15 years ago. I'm sorry, I cannot see my slide fully. But anyway, around 15 years ago, we have developed a very good spinning machines, yeah, for hollow fiber publications. And later, maybe around 10 years ago, we were able to make at that time, yeah, it is a very advanced spinning machines. So we were able to to produce what we call as a multi-bore capillary membrane. A capillary, not very small hollow fiber, but capillary. We can make it up to 2 millimeters spinner for a single bore like this. And in fact, this one actually contain of around 37 bores. So the membrane is becoming very strong and super hydrophilic, but also the use of polymer is becoming very efficient. So with this type of configuration, or with this development, and with the help of our very special potting system we developed, because this is giant membrane we developed in Indonesia. So we have patented this potting system. Actually, we have a very special way of potting the hollow fiber, and in fact, we were able to make this kind of large membrane, and this is around 24 inch in diameter with a 7 meter long length. Sorry. Oh, sorry. Yeah, and this type of membrane can produce 100 cubic meter per hour easily. So, and this membrane can be buried actually in the bottoms of the reservoir. And in fact, we were, yeah, this actually has been installed in one of palm oil industry in Kalimantan. And then we also use a different, a similar type or non-module membrane module for concentrations of nanochloropsis. And this is a feed actually, and this is the concentrate, and the water is reused back to the aquaculture system. So those kind of development, this type of membrane actually, is a very easy to use and it's a very simple. But recently we recognize some of the problem we have actually when we are talking about a very large application, for instance, above 1,000 cubic meter per hour. We cannot scale it up any longer. The maximum diameter we can use or we can produce actually is the 32 inch actually. Then probably the capacity is around 200 something cubic meter per hour. But in that approach, actually, we develop this kind of another version of non-modular membrane. Actually, this is modular, but anyway, what we mean as a non-modular here actually is a kind of simplicity. So the membrane is mounted in a simple way. So if we are talking about 1,000 cubic meter per hour capacity, so a normal modular membrane with usually the length, it has its length around 1 meter. So the system will be very complicated. So now we alter the length of the membrane. So based on our optimization, we actually have an optimum conditions around 4 meters length with the inner diameter of hollow fiber we developed by ourselves. So the outer diameter of a single part of this non-modular system is around 6 inch. So this 6-inch module with a 4-meter length, it consists around 150 square meters membrane area. And this capacity is around, let's say between 5 to 6 cubic meter per hour. It's very easy to get that kind of capacity. And all the input and output, the feed and the permit connection, we have a very special approach for that. We use a very recent development in what we call as a flexible quick fitting. And we have a very special technology for such kind. So allowing us to mount this type of sub-modules in arrangement like this one. This is content of 9 modules actually, 3 to the top, 3 to the sides, and then this is 9 module, and this one actually is block. So you do need to have a frame between module to modules. So the modules just pack, right? And then this kit is is arranged in this way. So this kit has a 9 module. The capacity is around 50 cubic meter per hour. Okay? So here we have 8 of this type of kit. We can easily arrange in a special way. So this 8 has a capacity around 400 cubic meter per hour. So the size is just 1 meter high and 2 meter in wide width and 4 meters in length. So it's a very, very compact module. So actually this is still, we can say as a modular membrane, but anyway, due to a very simple connection, yeah, a very simple arrangement of membrane module with large capacity, very large capacity. So this, we still want to call it as another version of non-modular membrane. This is our approach actually in Indonesia. So that's the way we develop our application. Then the idea, or the main idea actually, is to reduce the cost, because the cost of membrane sometimes is not very significant compared with the frame and connection, and because every module you have to have a probe, etc., blah 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 blah. So that's cost you really a lot. Yeah, but in this type of configuration, those kind of cost is almost nothing. Yeah. So because we have a single header for this kind of block, even though you have, let's say, 20 of this kind, so we can easily arrange in this way. Yeah. So this is what we call as a novel approach in non-modular membrane for Indonesian way. Let's say like that. So for those of you who don't have all those information, you can actually visit my research kit. I always put all those development actually in my research kit. I think that's all. Thank you. Helen?
Thank you, Professor Wenton, for a very timely presentation. So next, we move to our last speaker for this first section, Professor Hiroshi Yamamura. Professor Hiroshi Yamamura today will present about challenging membrane technologies for reuse of industrial wastewater. Please, Professor Yamamura, the time is yours.
Oh, can you hear my voice? And can you hear my, can you see my presentation?
Yes.
Okay.
Yes.
Is it working well? Okay.
You are using a double screen, right?
Yes.
That's correct. It's good.
Okay.
Great for.
Okay. Good morning, ladies and gentlemen. My name is Hiroshi Yamamura from Chuo University, Japan. Today, I'd like to thank to everybody to hear my presentation and make the chance to give my presentation. Actually, in 2020, we have just started the double degree program between the Chuo University and ITB. But unfortunately, as you know, the coronavirus prevents the start this project. But in future, we are collaborating with ITB students and ITB professors deeply for the collaboration research and the student exchange. So my today's topics is that the challenging of membrane technologies for reuse of industrial wastewater. So today, this is the contents of my presentation. First, let me speak about the current situation of Asian countries and the industrial park in the Asian countries. And then the second, we are talking about the technology needs in the Asian countries and industrial park. And finally, we want to introduce one of the research project, the fouling prevention by the bacillus activations. So first, let me show about the current situation of the Asian countries. As you know quite well, 2010, about 60% of the population is Asian people, Asian person. And even in the 2050, their percentage is still the 55%. So it means that the more than half of the population is Asian countries, okay? And in addition, the urbanization rates of the Asian countries, the red line, is now the rapidly increasing from 45% to the 65% in 2015. So the condition of the Asian country is like this. It's like a packed train in the Tokyo. So I think that in your country, I think you will be the packed in the train like the Tokyo. But now the situation is a little bit changing because of the coronavirus, but the situation is like this, okay? And also the Asian countries, including Japan, is facing many the flood by the typhoon, storm rain, intensive rain, and hurricanes. And I think you remember that the very serious typhoon, very serious the flood in the Thailand in 2013. Okay. And after this, the serious flood in Thailand, the Japanese companies often move their factory from low wetland to the higher location of altitude of 30 meters or more in order to avoid the flood damage. Okay, so there are Japanese companies moving from the lower location to the higher location because they want to avoid the flood damage. However, the highlands often face the water shortage due to the limited water resources. So because away from by moving from the lower wetland to the higher location, they are also away from the water resources like river or groundwaters. So I want to show the examples of the Patalganga Industrial Park. It is Indian countries. So Patalganga Industrial Park is located at near the Mumbai. This is India, and here is Patalganga Industrial Park. This park is very familiar for the Japanese company because the many Japanese company is building the factories in this Patalganga Industrial Park. However, the industrial park is facing the water resource shortage because the water demand is expected to increase in future due to rapid industrialization in India. If additional industrial water supply facilities are not prepared, the supply capacity is expected to decline to 50% of the total demand by 2030, resulting in a serious water shortage situation. So the water is now the limitation for the industrial park in the Indian country. And in addition, please look at this chart. This chart shows the industrial water usage percentage. So where they need the water is that the cooling water and the temperature control water. About 80% of the water is used for the cooling water and the temperature control. So that's why we have to make the cooling water from the wastewater if we want to reuse the wastewater. And the current, this slide shows the current status of the Patalganga wastewater treatment plant. This is the current treatment flow of the wastewater treatment plant. The first, the wastewater was the screened pond, coagulation, sedimentation, UASB, aeration pond, and the discharge. However, even though they are treated very well, but the condition of the treated water is like this. Can you see that the yellow colors, the water? This is not the influent. This is a discharged water. That's why the water quality of the discharged water is not so good. About COD is more than 400, and the TDS is still the 4,000. So we cannot use this discharged water for the cooling water because cooling water requires the COD is less than 1 milligram per liter and the TDS is less than 30 milligram per liter, far from the quality of the cooling water. So that's why we need the additional treatment process after the wastewater treatment process. So in this process, we have to install the biological treatment and solid separation and the NF or RO treatment for the desalination. So the biological treatment and solid liquid separation is is carried out by the membrane bioreactor, because membrane bioreactor contain the both biological and solid liquid separation. However, the TDS cannot be removed by the membrane bioreactor. So that's why we have to add the NF or RO membrane treatment process after the MBR process. So the problem is that the cost of the NF-RO membrane and MBR process, because only the NF and RO membrane cost about 100 yen per, more than 100 yen per square cubic meters. However, the required cost of the water supply in the industrial park is about 50 yen per cubic meters. So there is a large gap only between the NF-RO membrane. And we have to add the membrane bioreactor as well. So that's why we need the install of MBR and RO membrane for the water reuse, but they should not exceed the 48 yen per cubic meter. So this is a big problem for the installation of the advanced water treatment in the industrial waste or industrial park. So now actually we are now developing the method to reduce the NF-RO membrane cost. But today the time is very limited, so we want to introduce the research topics about the membrane bioreactor. So the membrane bioreactor is a very promising method because they can achieve the high quality of treated water and the small footprint. However, the major drawback of the membrane bioreactor is the membrane fouling. The membrane fouling is a decline of the water permeability due to the clogging of the pores by macromolecules. We have been studied about what kind of the component causing the membrane fouling, and we have found that the macromolecular organic matters, including the biopolymers, that causing the major fouling in the membrane bioreactor. So please look at these tables. This table summarizes the mechanisms of the fouling and their countermeasures. So please look at this line, the first line. The first line shows the mechanisms of the membrane fouling. So in the membrane bioreactor, we have there are many microorganisms, and these microorganisms generate the metabolites like EPS or SMP, or sometimes they decay and produce the SMPs. Okay, so such kind of the EPS or SMP is a macromolecules, colloidal materials, and then these materials is stuck on the membrane pores or the accumulating in the membrane pores. So this is a membrane foulings, occurrence of the membrane foulings. So to control this membrane fouling, we have several methods. The first method is that the control of sludge properties. If the specific microorganisms that can be grown in the bioreactors, that we can control the production of the EPS or SMP. But actually, it is very difficult because the control of sludge may affect the treatabilities. And it is very difficult to control the microorganisms as well. And the promising method is that we can optimize the operation conditions or chemical cleaning conditions or optimizing the membrane types or membrane characters. However, the optimization of the membrane or operation condition is also very difficult if the operation has started. Because after the starting the operations, we are very difficult to change the operation condition or change the membranes. Okay, so have to install this kind of the countermeasures have to install at the construction phase. Okay, that's why the many researchers has focusing on the control of the colloidal components. For example, to prevent the production of the EPS, the quorum quenching is now the very interesting topics. The column quenching is that can control the production of the EPS or SMP and decrease such kind of the metabolites. And the other method is that the decomposition of the EPS and SMP. This is also very promising. The decomposition, adsorption, and precipitation is a very this kind of the method is the conventional method, and we can install at any times, even after the operation has started. So we summarize the conventional decomposition method. For the decomposition, the ozonation is a very familiar, but ozonation generates the formation of the byproduct, and the adsorption, the ion exchange is also that can remove the biopolymers, but disadvantage is that the treatment of regenerated water is very difficult, and the ion exchange process is very complex. And the coagulation is also can reduce the biopolymer concentration. And this is very cheap and simple, but the increase of sludge is a very the big problem in a practical operation. So that's why we have focusing on the enzyme, biopolymer degrading enzyme. Enzyme is very interesting because they cut specific position of the organic structures. So if we can find out, if we can find the enzymes who can cut the biopolymer structures, we can cut the biopolymers and into the small pieces, and these small pieces can easily passing through the membrane pores without accumulating on the membrane. And some researchers has already tested the topics. Berg and Bay put protease and amylase into the sludge, and they clarified that enzyme can decompose the EPS. So that's why I thought that the enzyme can decrease the biopolymer concentration, and finally decrease the development of the membrane fouling. However, the problem is that the enzyme is a very high cost of the commercial enzyme and low stability of added enzyme in the mixed culture. So that's why I thought that if we can generate the enzyme by the microorganisms living in the sludge, so we can prevent the membrane fouling very easily and in a lower cost. So that's why we're focusing on the Bacillus species, because Bacillus species can produce the variety kind of the enzymes that break down sugars and proteins, and they are universally present in the water and the soil and even in the sludge. So that's why I thought that if we can activate the Bacillus living in the sludge, we can decrease the biopolymer concentration and prevent the membrane fouling. So we try to isolate the specific Bacillus from the sludge by using the biopolymer containing agars, then find out activation the additives to produce more enzymes from the Bacillus. So the Bacillus we isolated here called as the Bacillus A. So please remember Bacillus A. This is my Bacillus, okay? And my Bacillus is working well if the sum of the inorganic element is presented in the water. But without the additives, they didn't work very well. Okay. So it means that this kind of the additives is very essential element for the production of the enzymes. Okay. So I thought that if we add this activation additives into the sludge, the Bacillus A produce the enzyme and then decrease the biopolymer and prevent the membrane fouling. This is the strategy of my study. So we try to compare the effect of the additives. We operate two membrane bioreactors. One reactors at the additives, like this, and then compare the biopolymer concentration and progress of the membrane fouling. So this is the experimental conditions. The only in the run one that we add the activated powders. The amount is 100 milligram per day. The very, very tiny amount of the additives was added into the reactor one. Okay. The other condition is completely same, and the raw water quality is like this. And the point is that what is this raw water? Okay, so this raw water is the produced from the beverage company. We call it as a C beverage company, very famous company, and they wash the bottles like this, and then the washed waste solutions contain the carbohydrate and the nitrate. So we have to treat this carbohydrate and the nitrate by using the MVR. Then the treated water is used for the cooling water. This is the process of this C beverage company. Okay, this is analysis of the membrane foulant. I will skip this slides. Okay, so the first, I will show the results of the. I will show the result of the sludge properties, because we add the inorganic element every week. So we thought that MLSS and VSS-SS ratio will change the daily. However, as a result of the addition of the additives, the MLSS is not changed. The MLSS is around the 10,000 milligram per liters, and the ratio of the organic matter in the sludge is almost the same. So it means that additives didn't accumulate in the sludge tank. And
Professor Yamamura, 2 minutes left.
Okay, thank you. The microbial community structure analysis is like this. So please look for the Bacillus names in here. Can you find the Bacillus names? It means that the Bacillus is not dominant in the microbial community. So, but they exist in the reactors, very, very tiny amount, but it's not the dominant. And we also measure the count of the Bacillus A's in the reactor 1 and 2. Please look at this graph. The count of the Bacillus A is about 10 powers 9 only in the Bacillus A, only in the reactor A. But in the reactor 2, we cannot find any Bacillus. So it means that only reactor 1, the Bacillus A strains were detected through the run, and it was clarified that 10 powers 8 cells exist per 1 gram of the sludge. Okay, and as a result of the dominance of the Bacillus, we can the decrease of the submicron particles. The submicron particles is the major foulant of the membrane bioreactors. So in the run 1, the count is about 1/3 that of the run 2. So some micron particles are reduced in the system with increased Bacillus. The dissolved organic matter also decreased by the addition of the additives, and the biopolymer concentration also decreased by the addition of the additives. The 1/3 of the concentration can achieved by the addition of the additives. Okay. And polysaccharide and protein also can decrease to a large extent. So it means that we want to summarize that the addition of the inorganic additives can decrease the biopolymer concentration by generating the enzymes. Okay, then we think that we can prevent the membrane fouling to a large extent. Okay, so next I show the changes of the transmembrane pressure. So the red line shows the run 1, and the brown line shows the run 2. As you can see clearly in this graph, by the addition of the additives, the membrane fouling was reduced to a large extent. Okay, in the round one, we cannot see any fouling development. However, in the round two, the severe fouling development was seen in this graph. Okay, so it means that the addition of the inorganic additives working very well for the prevention of the membrane fouling. So this is the conclusion of my studies. Biopolymer was reduced by the domination of the Bacillus A, and prevention of the membrane fouling was verified. And the activators, additives, inorganic additives are readily available anywhere, and 0.1% of MLSS level is added once daily. It is very inexpensive approach compared to the enzyme injection. So finally, we want to show that the resource needs, because the human resource is a very, very important resource for the operation of the maintenance of the infrastructure. That's why the primary challenge for the industrial wastewater treatment is that who will manage the operation and the maintenance, especially in the industrial treatment plant, because the labor cost is very, very expensive compared for the conventional the domestic wastewater treatment plant. So that's why the challenging technology for the operation and the maintenance of the membrane treatment is very, very important topics for the successful and sustainable management of the industrial wastewater. So that's why today I introduced the membrane bioreactor additives for the fouling prevention. And we are also doing the research about artificial intelligence control of the membrane process. Thank you very much for your attention.
Okay, thank you, Professor Hiroshi Yamamura, for a very interesting presentation. Now we move to the panel discussion one. Okay, so I already have several questions here. The first question for Professor Yamamoto. So the questions come from Batam, Indonesia. So in Batam is actually a small island, yeah, in small islands with 2 million people. And in Batam, they have a lot of industrial estates. So Erigana asked Professor Yamamoto, what kind of reused industrial water can actually disrupt the lives of human population in that small islands like Batam? Please, Professor Yamamoto.
Okay, yes. Disrupting case. This means, right?
Yes.
So I can't catch fully of this question, but if you're talking about industrial water, so this industrial estate is there, then we have a large extent of the influence of the industrial water discharge from the factory. And if we utilize any type of the reuse technology, then this, generally speaking, this gives mitigation of the industrial effluent to the environment. Mitigation means that in terms of the reduction of the water discharge, wastewater discharge to the environment. So in this sense, if you're talking about the discharge aspect to the environment, reuse technology gives a large merit on that. However, we need to consider the energy consumption or total system analysis of the total energy consumption or life cycle energy consumption or CO2 emission. To the then this gives a kind of selection of the technology to that regions. So I can't say which type of the reuse technology is good and bad, or effective or non-effective. in each case. But and so we need to consider this kind, of course, we need to consider this kind of aspect in terms of the total emission and in terms of the CO2 emission or energy consumption. Yes. But in terms of the water discharge, any reuse technology can give merit to each industry. Is it right? Is it all right?
Yes, Professor, yes. Okay. Thank you, Professor Yamamoto, for the response. Next questions for Professor Wenton. So the question is how if combination of electrochemistry treatment in wastewater with the membrane for water reuse?
Okay. Helen, can you hear me?
Yes, Prof. Yes.
Yeah, big problem with my connection. But anyway, this electrochemical combination with membrane, I think it's possible with electroplating wastewater, for instance, or maybe some other application. It is possible. Thank you.
Okay. Thank you for the response, Professor Wenton. And next question for Professor Yamamura. The questions comes from Professor Chandra. How does the quorum quenching may be used in the practical application to reduce the biofouling in MBR?
Thank you very much. Actually, my topics is not the quorum quenching, but I thought that I have read many papers about the quorum quenching, and they are now the many researchers try to find out the quorum quenching the materials, the chemicals, and then these chemicals was the added to the reactor or the insight into the membranes is a very interesting topics. So now they are developing the many methods to activate the quorum quenching effect. Sorry, I'm not the professional of the quorum quenching.
Okay, thank you, Professor Yamamura. We still have another questions. Yes, okay. So next for Professor Yamamoto. So in line with the population growth, which is also followed by the increase in various activities and also require more water and coupled with the climate change, what can people living on small islands and coastal areas anticipate to deal with this?
Okay, thank you for the question. If we're talking about the small islands, and then this kind of is typically happened in Indonesia, I think small system. I think we consider a small system. Of course, this can include advanced technologies, but this advanced technology should be coupled with natural energy like solar energy and wind energy and so on. Or some. So if we consider this kind of some autonomous system in a small islands, and then there's a variety of the technology now it's on the list. And then if we're talking about the reuse technology or water use or water technologies, and then you can combine water technology coupling with this kind of energy supply or other supply issues. So this means a chemical supply is, if we're talking about the supply chain crisis, which might happen in future, then chemical treatment or chemical requirement, maybe we need to avoid as much as possible. So I think if we're talking about operational maintenance, then some small requirement of the maintenance in terms of the chemical supply is preferable for the small island, I think. Thank you.
Okay, thank you, Professor Yamamoto. Next question is for Professor Wenton. Is the membrane bioreactor has the ability to separate mixed waste? Actually, the industrial waste and the household waste that mostly found near seashore.
Okay. Yes, of course, membrane barrier can always do that. But anyway, it's better to separate between industrial waste and household waste. If we are talking about bioreactor, actually, we are talking about biological degradations. That is something to do with organic. But some industrial water sometimes contains inorganic. But anyway, if you cannot avoid that, then probably you may have some other treatments after membrane bioreactor. Also using membrane is possible. Thank you.
Okay, maybe to extend the question, what is the effect of the inorganic in the membrane bioreactor? So if we put the inorganic also in the membrane bioreactor, what will happen?
Yeah, but, the bioreactor cannot biodegrade the inorganic, right?
Yes.
Then if you are using ultrafiltrations for membrane bioreactor, then the inorganic will be passed. Will pass the membrane and go to the permeate side. Then your permeate still contain inorganic. But if that inorganic from probably electroplating energy, that's very difficult. Yeah, it's very dangerous. But anyway, in that such case, it's better to separate between industrial waste and household waste. Then industrial waste, you can use maybe electrochemicals combined with membranes, electrodialysis or whatever. Yeah, or maybe electroflocculation, coagulation, and then combined with ultrafiltration. That would be better for industrial waste coming from inorganic contaminants like electroplating industry. Yeah.
Okay,
Thank you.
Dr. Wenton. Next question is for Professor Yamamura. How to control the decomposition of EPS to avoid more fouling on the membrane surface by adding the enzymes?
Okay, thank you very much.
So how is the connection between enzymes and EPS, Professor?
Thank you very much for your question. The EPS, the molecular size of the EPS is very big. So that's why the small bacteria cannot eat directly. But if the enzyme was presented in the waters, the enzyme can cut the EPS to the small pieces of the organic matters. Then the small microorganisms can eat directly the pieces of the EPS. So that's why after cutting the EPS by the enzyme, then the small microorganisms that can eat these small pieces, then that reduce the organic concentration. So that's why by adding the enzymes, the amount of the organic matters also decrease. Then prevent the accumulation of such the macromolecules and organic matters on the membrane surface. So this is the hypothesis why the enzyme working well for the prevention of the membrane fouling. Thank you.
Thank you, Professor Yamamura. Very interesting. Next question. We still have another question. Okay, so Professor Sasongko from ITB asks, Professor Yamamoto, do you have any experience with water use in coal mine? And what is the typical cost per ton of coal? So Professor Yamamoto, if you have any data about the water use in coal mine.
Thank you. Because I mentioned about more than 2,000 cases in Japan. Our center, Water Use Promotion Center, has experience in water use promotion. However, our center has no case study in a coal mine in Japan. So, and also if this coal mine is very, I think variety of the discharge wastewater happens, and depending on the location, depending on the type of coal, type of mine, or geographical aspect and so on. So I think it's very difficult to generally answer the cost of this cost of treatment. at least we need to know the wastewater quality and then the situation in or condition, other conditions in that area. So this is very, very difficult question to answer. This is my answer. Thank you.
Very specific. Okay. Thank you, Professor Yamamoto. Maybe Professor Sasongko need to learn more about this from other sources, because this one is very specific for the coal mine. Okay, next questions for Professor Wenton about the large membrane modules, maybe the non-modular membrane modules. How to do CIP, the cleaning in place for the large membrane module, for the large capacity of membrane module?
Okay, it's just the same with other membrane modules. Even it's easier because this is a cleaning that only using a single header from the permanent side. So you can still use cleaning in place. You can still use chemically enhanced backwash in this kind of modules. Yeah, that's all. Thank you.
Okay, so just the usual chemically enhanced backwash. Okay. Next for Professor Yamamura. So this is regarding the organic molecules. So if we break down the organic molecules into the smaller pieces and allow it pass through MBR membranes, we still have to deal with the organic accumulation on the downstream of RO, if any RO after the MBR. So of course, if there is no RO downstream, there is a good solution. But what if we have RO after the MBR? Is it just shift the problem to the RO from MBR? Please, Professor Yamamura.
Okay, thank you very much. This is very important questions, as have been said. Yes, we have also tested the downstream RO treatment in the lab scale, and we have found that by applying this MBR treatment, that we can decrease the RO fouling as well, because some professor said that the foulants of the RO and MBR is very similar. So that's why we can reduce such kind of the biopolymers before the RO membrane, that we can decrease the development of the RO fouling as well. And as I said before, the previous questions, the organic contents also decrease by the addition of the enzyme, because the enzyme can cut the biopolymers. Then the biopolymers was consumed by the microorganisms. So that's why the fouling potential of the RO membrane can decrease a little, decrease by the addition of the enzymes in the MBR. So, but we have to test this process by the practical situation. This is only the lab scale experiment. So we have to need the practical operations of the process. Thank you very much.
Okay, thank you, Professor Yamamura. So even though the organic molecules can also forms the fouling in the RO, but that molecules actually have been consumed by the bacteria in the MBR. Yeah, so basically after the MBR, the molecules are greatly reduced in number. Am I correct, Professor Yamamura?
Yeah, that's right. Yeah, thank you very much. Yep.
Thank you. Next question. Okay, so next question is for Professor Wenton. This question about the modular membrane. How was the modular membrane can absorb wastewater with the high salination like in Israel? Maybe not absorb, yeah. Maybe filter wastewater with high salination in Israel. How to scale up this design of membrane to wastewater manufacture?
Okay, thank you. So absorb wastewater from with the high salination.
Salinity.
So yeah, this non-modular membrane actually is an ultrafiltration, not RO. So it cannot handle feed with high salt concentrations. But if you're talking about seawater, for instance, this type of module, this type of membrane, what we call as non-modular membrane, is a very ideal design for pre-treatment of seawater reverse osmosis. Usually now they are also using, say, ultrafiltration membrane, but anyway, in the usual way, in a normal design, what we call as normal design is a modular design. So this non-modular actually is a very simple and compact. It's very easy to operate. So in that case, if we are talking about high salinity water, yeah, whatever it is, especially seawater, then this type of non-modular membrane can be used for pre-treating USC water desalination plant. And then the next question is how to scale up our design membrane. This non-modular membrane, you don't need to scale up. It's very easy. So you can actually buy it with the capacity only. Just say the capacity, and then you have the modules. It is very simple one. Thank you.
Okay, Professor Wentan, maybe to expand the question, the modular membrane has, I think, has a huge dimension. Yeah. Do you encounter any problem with the pressure drop or hydrodynamic?
Yeah, that's a very good question. So we have very special design in the lumens of the hollow fiber. Yeah, in relation to the length of the membranes. Yeah, and also of course, in this case, we always use cross flow in operation, not dead end, not even a semi cross flow, just cross flow. So actually, we are expecting of cross flow around 0.5 meter per second. So in that case, pressure drop can be quite high. But anyway, so that's why I told that in my talk that this lumen diameter, even though it's a multi-bore, it's quite big actually. So based on our optimization anyway, earlier we have a design of a 6 meter length in membrane, so 7 meter length in module. But anyway, now our newest product actually, the length of it is only 4 meters. And that's the optimum one, including some consideration from the economic point of view, especially with the availability of piping, yeah, we have in the market. Thank you.
Thank you. Okay, the next question for Professor Yamamoto. As we know, the RO system is currently the best in water treatment and is quite expensive as well. Is the RO membrane filter material can be regarded as cheap so that it can be used by general public easily? So that's in the in the term of using RO for general public. Yeah, is it how about the price? How about the price? Is it pretty cheap for public usage?
Okay, so if you're talking about membrane application, in this case it's RO system, we need to consider the capital cost, capex, and operation cost. And then anyhow, if of course RO desalination, maybe someone considers some expensive, but it depends on the water shortage, degree of the water shortage in the area. Then now RO desalination, which is applied practically in the world, is a cost of this membrane cost is not so expensive at all. So in this case, because membrane system has some merit of scale of merit production, standardized. So of course, and then also the membrane itself, material cost is rather cheap comparing to the moduling cost or system construction cost. But anyhow, in this capex, in the capital cost case, I think I don't think it's so expensive in terms if we're talking about the use stream, like in Singapore. But still, we need to reduce operation cost, OPEX, due to the energy consumption issues. Then also some effective design or rational design, total design of reduce chemical requirement cost and then energy cost and so on and so on. Then there's a much room for the reduction of this kind of this cost reduction in total. But I think the point is not rather membrane itself. Of course, you have an innovative membrane. Of course, it's very, very promising, but this gives first higher cost rather than the commercially available membrane itself. And it depends on the market expansion. But anyhow, if we're talking about the present status of the total cost distribution in our system, membrane material itself is not so significant. This is my question, my answer.
Thank you. Now, next question is for Professor Yamamura. Regarding the additive used in the MBR, what is the additive you use in the experiment? And why did you conclude that Bacillus is the predominant in the process, even though based on the NGS results, the amount of Bacillus was less dominant than other bacteria?
Okay, thank you very much for the question. The first question is that the additives we used is the mixture of the inorganic elements like silicate, iron, aluminum, calcium, magnesium, manganese. But we don't add this kind of the chemicals. We used the iron slug powders, because iron slug powders contain all of these elements and can get the very cheap. So we use the iron slug powders for as additives. And the second question is that why we conclude the Bacillus is a predominant in the process? Yeah, that's right. As I said, finally the Bacillus, the count is about 0.001% of the total bacteria count. So it means that very, very tiny percentage of the bacteria working very well for the reduction of the biopolymer. But unfortunately, as the health sensei said, we cannot conclude the Bacillus working, only the Bacillus working for the reduction of the biopolymer. So it is very difficult to prove the Bacillus working Bacillus reduce the biopolymers. Please consider that the Nitrobacter can reduce the ammoniums, but I think that it is very difficult to prove the Nitrobacter only working well. So we have to prove, but it is very difficult. So please give me the comment or ideas to prove the Bacillus working for the reduction of the biopolymers. It's very difficult. The question is very difficult to prove this process.
Okay, maybe one more question from me, Professor Yamamura. Why did you use Bacillus strain A? What happened if you use Bacillus strain B and add some more additives to that strain B?
Thank you very much. So I think the Bacillus strain B also working for the reduction of the biopolymers, but as a result of the many lab research, the Bacillus A generate the enzymes for the reduction of the biopolymers. So that's why we focusing on the Bacillus A. But I think that there is the different types of the batteries. So now we are still isolating the different types of the batteries, like depending on the temperature or depending on the biopolymer types. So we are now the isolating the different types of the batteries. Thank you very much.
Okay. We still have another questions, but unfortunately we have to end these sessions due to the time limit. Thank you for the answers and explanation from the professors. And also thank you for the enthusiasm of the participant. We will have 15 minutes break and we will continue to session 2 after the break. Thank you.
Helen,
Yes.
it may be Professor Wenton will leave, so we may take the pictures of us. I mean, with the Professor Wenton, probably Professor Wenton may not join until the end.
Okay, so
Thank you.
maybe we can open our video. Yeah. Open our video, and the committee, can you please take a picture of us together?
Hello, from the committee.
Okay, be ready.
Okay.
Just
3, 2, 1, cheers. Okay, it's done.
Thank you all.
okay.
So see you in the next 15 minutes.
Okay, thank you.
Thank you, everyone. Thank you.
Hello, ladies and gentlemen. The break session is over. After this, the main session of this event will be continued. Now, I would like to invite Mrs. Helen to begin the second half of the main session. Mrs. Helen, the time is yours.
Thank you, Fatur. Okay, so now we are in the second session today. In the second session, we will have two speakers. The first one is Mr. Toru Nakano from OrganoCorp. So Mr. Toru Nakano is an expert of physical chemical treatment of water and wastewater. Mr. Toru Nakano also has developed silica removal system to increase RO recovery ratio and fluoride recovery system for semiconductor manufacturing industries. Today, he will give us lecture and presentation on these two topics. And the second speaker is Mr. Dr. Kazuhisa Mimura. Dr. Kazuhisa Mimura is the Technical Research and Development Center in Sankey Engineering. His main current work is basic research for water treatment in general, and he has been involved in planning, design, construction, provision of public sewage treatment plant. Okay, to begin with, Mr. Toru Nakano, please, the time is yours.
Yes, can you hear me?
Yes.
And can you see my
Yes,
presentation?
clearly.
Yes,
Okay.
yes.
Okay, good morning, everyone. I'm Toru Nakano from Organo Corporation in Japan. I'm responsible for wastewater reclaim and ZLD system development. I'm very glad to be here today. I'd like to thank you for kindly inviting me to speak here today. The purpose of my presentation is to explain about our wastewater reclaim and ZLD system. We developed wastewater reclaim system, especially pre-treatment method for RO. My presentation will help to solve a problem that water recovery rate is low. Okay, here is the outline of my presentation. First of all, let me talk about background and objective of ZLD. Next, conventional ZLD system. And then I'll talk about a pre-treatment method for RO. I'll be focusing on silica removal for RO today. And next, I'll show you our pre-treatment method and operating data at semiconductor factory in Japan. At another topics, I will explain the recovery of fluoride by agitated crystallizer. First, let me talk about the background and objective of ZLD. As you know, in recent years, ZLD and MLD technology has been strongly required. But these methods are more costly than water discharge. So why do we have to achieve ZLD? These are the general drivers of ZLD. Stricter regulations on wastewater disposal, especially China and India. Even in Japan, large semiconductor factories must reduce water intake and wastewater discharge as much as possible. Water intake and discharge regulations are becoming stricter year by year. So we must increase the water recovery rate even if the cost is high. Now I'd like to move on the conventional ZLD process. This video shows RO concentration and evaporation example. Wastewater, VWRO, SWRO, concentrator, and crystallizer or evaporation pond, and solid disposal. If we must achieve ZLD, we will eventually need an evaporator. Because the evaporators capex and opex are extremely high, we need to reduce the inlet water volume of evaporator as much as possible. A typical technique is RO, which is much cheaper. In order to stably operate the RO, it is necessary to properly pre-treat the hardness and silica. This figure shows silica and calcium concentration. The vertical line is silica concentration. The horizontal is calcium concentration. This area does not require any pre-treatment, but the upper right area is needed the appropriate pre-treatment. To achieve a reliable high recovery ROZLD system, the suitable pre-treatment is required, such as lime or soda ash softening and ion exchange, silica removal. We could extend the application range of RO by developing a variety of pre-treatment techniques. And I will not explain in detail today. We can concentrate the wastewater despite high osmotic pressure by introducing the high pressure RO, like UHP ultra high pressure RO or disk RO. And we should introduce efficient thermal concentrator. Next, this table shows our pre-treatment method for silica removal. Number one is adding anti-scalant. Number two is adding acid before RO. The scale risk by hardness is lower, but this is not suitable for very high silica concentration. Number three is adding alkali before RO. The risk of biofouling is lower, but we must reduce the hardness. Number four is silica removal by coagulant. There is no concentration limit, but large equipment is required. Each of these methods has advantages and disadvantages, so we have to choose the methods depending on circumstance. Next, I'd like to move on our ZLD system. This video shows the example of our ZLD system. The industrial wastewater equalization tank and lime or soda ash softening and silica removal and ultrafiltration, ion exchange resin, RO, SWRO, UHPRO if you need it, and evaporator and crystallizer. Silica removal is the important point of today's presentation. To operate the RO incorporated ZLD system at high recovery rate, extensive pretreatment such as chemical softening, pH adjustment are required. The OPEX of thermal concentration are very high due to the high energy consumption. It is required to reduce the quantity of the brine, which is sent to an evaporator as much as possible. Next, I'm going to explain the silica removal. As you know, the silica exists widely in nature, especially in Japan, and it is one of the causative substances of RO clotting. The solubility is around 120 ppm in room temperature and neutral pH. We have some methods to prevent the RO clotting by silica. Today, we will introduce you to operating data. As you know, high efficiency RO system, HERO, is widely known to be applicable to high concentration silica. Under alkali conditions, the solubility of silica is high, but the solubility of calcium carbonate is sharply decreased under alkali conditions. So the softening method, for example, ion exchange resin, is required. On the other hand, silica could be removed by coagulation and sedimentation. We suggested MLD system with silica removal by adding a coagulant named Olgafix DS02. We have been operating an actual plant since September 2018. Next, I will introduce you to operating data. We have done on-site tests from April to October 2018 at semiconductor factory in Japan. The raw water is raw brine of industrial water. we introduced raw water to the softener. The softener is strong acid-cation exchange resin, so a small amount of calcium leaks to RO. Next, we adjust the pH around 11 in the raw water tank. And we introduced to RO. This figure shows the flux of RO membrane. The vertical line is flux, and the horizontal is operating time. The concentration of silica is about 800 milligram per liter and 1,200 milligram per liter. The concentration is adjusted by changing recovery rate. If the calcium concentration of our brine is about 1 milligram per liter, the membrane is clogged and reduces the flux sharply. If the calcium concentration is under 0.1 milligram per liter at our brine, the flux is stable. The silica concentration is around 1,200 milligram per liter. The calcium was leaked if we use the strong acid-cation exchange resin for softening, but the weak acid-cation exchange resin could reduce the calcium below 0.1 milligram per liter. Flux was stable for a month, and the silica concentration is 1,200 milligram per liter. It is important to keep the hardness low in order to operate the RO stably in alkali conditions. To prevent the calcium carbonate scaling, we have some solutions. Softening by weak acid-cation exchange resin. Another way is adding anti-scalant, and decarboxylation is preventing scale by decreasing the bicarbonate ion. Next, this figure is a block flow of the actual plant of silica removal by coagulant. We have been operating actual plant since September 2018. The red number is the water volume ratio, just ratio. For example, the inlet water volume is 1,000. This factory was required to reduce water intake and discharge as much as possible. So the recovery rate of the system after number one RO is about 76% because the silica concentration is about 250 milligram per liter. So we cannot concentrate by RO anymore. So we installed this silica removal, ultrafiltration, and RO system. The system can increase the recovery ratio from 76% to 88%. So we can reduce the water intake and discharge. And this video shows the flow of silica removal by coagulation. Inlet silica concentration is about 200 milligram per liter actually. We are adding the chemicals named Olgafix DSL2 for silica removal. And we added some coagulant and polymer. Silica floc is hard to flocculate, so we selected the dedicated polymer. Silica concentration was decreased by adding chemicals to 60 to 70 milligram per liter stably. If we added more chemicals, we can reduce the concentration of silica below 10 milligram per liter. But in this case, it is enough that the silica concentration is around 60 milligram per liter. And we added the coagulant, ferric chloride, before UF to prevent the clogging by polymer. And the waste was able to be more concentrated by RO, about 3 times concentration. And this figure shows the transmembrane pressure with a UF, which is installed after coagulation. During the trial operation, the polymer dosage is too much, so the pressure becomes high. Now, when we adjust the dosage of chemicals, the pressure is stable for half a year. This figure shows RO permeate flow rate. The RO is operated at constant pressure, so RO flow rate is stable for half a year without clogging. We have not washed the RO with chemicals. And this video shows the recovery rate of the system. We got the recovery rate around 50% stably. If I achieve the 50% recovery rate at this system, the total system recovery rate is from 76% to 88%. Finally, I move on to summary. So we should choose these methods according to the circumstance for silica removal. In general, the recovery rate is higher to the left, but the cost is lower to the right. The coagulation system can reduce silica concentration to lower, but the chemical cost is a little high. An alkali RO system can achieve high recovery rate, but if the hardness is too high, the cost for softening becomes high. The acidic RO system is low cost, but silica concentration limit is around 400 milligram per liter. Silica removal system by adding chemicals is operating well in general. Today I introduced you only silica removal methods. We developed the high recovery system, not only silica removal, but also hardness and the high pressure RO system. We are planning to do business in Southeast Asia using these methods. Next, I would like to make one more presentation, a short presentation as titled Recovery of Fluoride from HF Wastewater in an Agitated Crystallizer. Let me first give you the background. From the semiconductor factory, a large volume of hydrofluoric acid containing wastewater is generated. Concentrated HF wastewater is originating from etching process, and the concentrated HF is disposed as waste liquid. This is a conventional fluoride removal method. Fluoride is treated by calcium fluoride, precipitation, and coagulation. A large amount of sludge is discharged from this process, and this sludge is not suitable for uses due to the many impurities, coagulant and fluctuant. But the recovery of fluoride is required recently. Using crystallization method to recover fluoride as calcium fluoride crystal is possible. Calcium fluoride crystallization mechanism is shown at this figure. Seed crystals are put in the reactor preliminarily. Wastewater containing fluoride and calcium reagent are brought in where she is fluidizing. Fluoride and calcium reacts on the sheet crystal, and the crystal grows gradually. Grown crystals referred to pellets are able to recover. Actually, in using crystallization method, fluidized bed reactor is used for diluted HF, which concentration is less than 1,000 milligram per liter. However, it is difficult to apply it to the concentration HF wastewater, which concentration is several percent. As a result, we developed the agitated crystallizer named EcoCrystal. The schematic overview of EcoCrystal is shown in this figure. An agitator and a draft tube are attached to the crystallizer. Seed crystals are added into the crystallizer and kept fluidization by agitating. HF wastewater is introduced near the impeller. Calcium chloride and sodium hydroxide are introduced by the same way. Fluoride and calcium reacts to form calcium fluoride crystals on the sheets. Grown calcium fluoride pellets are withdrawn from the bottom of vessel. We can use this system at room temperature, and heating is unnecessary. A particle size is 30 to 80 micrometer. And the first equipment has been operated in semiconductor factory in Japan. The reactor is shown in the picture. The diameter is 2.3 meter, and the height is 2.3 meter. This is just a scat on the reactor. Influent wastewater, which is less than 9%, was treated. After the first unit, we delivered several larger units to another customers. Then I will describe the performance of the first equipment. The recovery ratio is 90% or more. The purity of calcium fluoride is 96.5%. The moisture content is 6.6%. The average particle size is 52 micrometer. So the calcium fluoride is easy to dewater. And then this is the same images of calcium fluoride are shown. The seed crystals are shown in this image. These surfaces lack smoothness and they are irregular in size. On the other hand, recovered pellets are rounded and regular in size. In addition, the surface of grown crystal is shown. There are fine particles on the surface of grown crystals. It appears that seed crystal grows not only by reaction on themselves, but by trapping the fine particles. Finally, it is shown in the figure that the system of fluoride recovery. Amount of HF wastewater is treated in the crystallizer, and the calcium fluoride pellet is recovered.
Mr. Nakano, excuse me, 2 minutes left.
Okay, thank you.
Thank you.
Sorry, the chime is ringing in Japan. The pellets are reprocessed in HF plant for HF reagent or fluoride chemical project. The HF is used at semiconductor plant. The fluoride recycle system is performed in this way. Now, amount of recovered calcium fluoride is several thousand tons per year now. So we established the fluoride recycle system. That's all. Thank you for your attention.
Thank you very much, Mr. Nakano, for the presentations. Now we move to our last speaker today, Dr. Kazuhisa Mimura. Dr. Kazuhisa Mimura today will present about the practical application of original biological treatment and filtration technologies for water reuse. Dr. Mimura, please, the time is yours.
Yes. So can't see and hear?
Yes, we can see it.
Clearly.
Okay. My name is Kazuhisa Mimura. Good morning, ladies and gentlemen. My name is Kazuhisa Mimura from Sanke Engineering. Thank you for a kind introduction. And Dr. Chandra, thank you very much for invitation to this meeting. But I'm very nervous because I'm embarrassed.
It's okay. It's okay, Murasa. No.
Sorry. And so, in my part, I'm going to present 3 samples of actual water reuse technology and application. So 1, MBR for building wastewater reuse. 2, installation of urban river and waterway by advanced wastewater treatment. 3, aerobic biofilter for pre-treatment of water use. So, but I'm sorry for my English very poor. Then I'm going to show them by 10 minutes movie film on Zoom sharing. If you had to watch, sorry, had to watch and go directly to this YouTube URL. Sorry. Let's start at film. See you later, 10 minutes later.
Chapter 1. MBR for Building Water Reuse. The development of new water supply sources has become more expensive in populated areas, especially in urban areas, and the concentration of buildings has
So
led to
you haven't shared the
density. The decrease in drainage and the need for temporary
I'm sorry.
storage of rainwater have led to the requirement of installation of gray water systems as water reclamation facilities as well as Chapter 1. MBR for Building Water Reuse. The development of new water supply sources has become more expensive in populated areas, especially in urban areas, and the concentration of buildings has led to a shortage of sewer capacity. The decrease in drainage and the need for temporary storage of rainwater have led to the requirement of installation of gray water systems as water reclamation facilities as well as rainwater infiltration facilities at the time of large-scale urban development. MBR, that's membrane bioreactor system, is very well suited for gray water systems. The main reason is that the water treated by the activated sludge is extremely clear and safe because it is obtained by passing through membrane. In addition, the maintenance of the treatment system is very easy, and thus does not require specialized engineers. Low ceiling. The other one, in the inline type, the activated sludge is injected by pumps into vessels with built-in membrane modules outside the aeration tanks. This pumping pressure allows the water to pass through membrane and drain out of the vessel. As the number of buildings increases, the processing capacity can be adjusted freely by increasing the number of vessels.
Chapter 2. Restoration of Urban River and Waterway by Advanced Wastewater Treatment. The Tokyo metropolitan government has been making efforts to restore and improve habitat and water quality of the riparian environment. A number of projects employing advanced wastewater treatment have contributed to this end. The over 40,000 ton a day of advanced treated wastewater is fed as the source water into Nobi Dome Waterway, Tamagawa, and Senkawa channels. From Tamagawa Juriua Water Reclamation Center, sewage treatment plant, at the upstream of Tama River. The water of those waterways and channels had stagnated water flow over a long time. But now, the advanced treated wastewater makes bobbling flow in the streams, and provides plenitude and comfort to people, and are used as a place of recreation and relaxation for the Tokyo residents. This sewage treatment plant consists of anaerobic anoxic process, sand filter and ozonation. The anaerobic anoxic process, a kind of activated sludge system, can remove a large part of organic matter, nitrogen, and phosphorus from sewage. Thereafter, the sand filtration can remove a small residual particle matter with a little coagulant. The kind of this sand filter is an upflow, moving bed type. The main feature is washing of filter bed by the airlift mechanism. The airlift washing can enable uninterrupted operation, which offers a number of advantages compared to a conventional backwash system. This sand filter is a very compact filter without moving parts, rinsing water supply tanks pumps, or automatic backwashing system. So that, this sand filter is available as units to be built into concrete tanks, or as freestanding units in steel, which is easily installed into the existing plants because it only needs supply pumps and air sources for airlift. Thus, the amount of treatment can be finely designed freestanding units in steel. This kind of sand filter is not only for sewage treatment, but also is ideal for water reclamation facilities themselves, or as a pre-treatment facility for more advanced reclamation facilities. And the further ozonation sterilizes and removes odor and color, so that the water becomes almost as good as drinking water. It is only because the water is treated in this way that it can be fed into waterways or channels, where people directly touch that water. Sand filtration, ozonation and, if necessary, activated carbon adsorption, are very basic water reuse technologies. Since the reused water treated in this way is extremely clear, colorless, and safe, it is used not only for the restoration of waterways and channels as in this case, but also for gray water system, sprinkling water in parks, washing in factories, and various other applications. Chapter 3. Aerobic Biofilter for Pretreatment of Water Reuse. In Susaki City, the sewage treatment plant has been renovated from the conventional activated sludge, which is an extended aeration system, to the entirely new plant with the concept to save energy and labor. This plant is composed of a settling tank, DHS, which is an advanced trickling filter, and further aerobic biofilter with moving bed. In the plant, the inflow sewage, from which large particulate matter was removed by settling tank, flows naturally downstream inside DHS without aeration or agitation, and most of organic matter and ammonia is removed. The DHS treated water is pumped up to the top of aerobic biofilter, where residual organic, particulate matter and ammonia is almost perfectly removed. DHS is an advanced trickling filter, in which caged sponge cubes are filled upon some layers. This sponge cubes can hold much water unlike stones of conventional trickling filter. Therefore, within about a quarter HRT of a conventional activated sludge system. DHS alone can perform almost as well as activated sludge system. However, DHS is unfortunately not always resistant to rapid fluctuations in processing conditions. An aerobic biofilter is a stand-alone tank with aerobic biological treatment and filtration function. Therefore, it can treat relatively high concentration sewage with using less energy than the activated sludge process, and can purify low concentration wastewater at high speed. In Suisaki plant, this aerobic biofilter can stabilize DHS treated water in the event of a temporary decline in the performance of DHS, and at the same time can make it clearer at very high speed. The filter bed of this aerobic biofilter is moving bed by airlift washing system instead of a conventional complex backwash mechanism. Therefore, this moving bed aerobic biofilter is operated with little or no more maintenance, and can be easily installed in existing water treatment plant. Thus, this moving bed aerobic biofilter alone is used just not only for advanced treatment of sewage, but also for making the water to be reused, for example, for irrigation, fish pond, and industrial water.
Okay, thank you. Thank you. Thank you. At last, just a moment. Can you hear my can you watch my presentation?
Yes, yes, yes.
Thank you very much. At last, I show the characteristic of aerobic biofilter by comparing with sand filter. Please watch this table. As the film says, the aerobic biofilter aerobic biofilter is the solid removal and organic matter, ammonia degradation are performed in the single tank at the same time and fairly quickly, though not as quickly as just only filtration. Thus, the principle is very simple, very clear, quite clear. That is, when particle is separated by and filter bed, organic matter and ammonia first penetrated into biofilm, and next their aerobic biodegradation. So that such is the reason why the aerobic biofilter is well suitable for the pre-treatment for water-use systems. So I have more times, but my presentation is that's all. Thanks for your attention.
Thank you.
Okay. Dr. Mimura, thank you for the presentations
Thank you
and
very much.
the video on YouTube. Very interesting video. Okay, so next we're gonna move to the panel discussion, the second panel discussion.
Yes.
Okay, I'm waiting for the questions list. Okay. So first questions is for Mr. Toru Nakano, yeah?
Yes.
How is the benefit cost analysis of silica removal and also calcium removal in the RO system? What factors should be considered before applying the system?
Yes. Okay. This customer desperately needed to reduce their water intake and their wastewater discharge. So they had to increase the water recovery rate due to the strict limits placed on water discharge and water intake. So the chemical cost of this method is a little high compared with water discharge, but they have to achieve the high water recovery ratio. But this system is less expensive than another method. For example, added dolomite or some other chemicals. So, and we are also developing a method of recycling our chemicals. So we try to reduce the cost of this system, but our customer is needed to reduce their water intake and water discharge. So that we should consider before applying the system that the cost merit and the needed of our customers' demand.
Okay, thank you. So now the question is still for Mr. Nakano. Can you please explain or maybe share about the RO cleaning chemicals for the high recovery RO in silica removal? So to remove silica in high recovery RO, how to remove the silica?
Yes, if the RO is clogged by silica or other organic compounds, we wash the RO by some alkali and at pH 12, around pH 12. And if the RO is clogged by other heavy metals or calcium carbonate, we wash the RO membrane by citric acid or hydrochloric acid around pH 2.
Okay. And regarding the impurities during the removal of fluoride, what impurities should be considered in removing fluoride in the fluidized system?
We consider the impurities which is react to calcium. For example, silica or some heavy metals, aluminum or phosphate. If the impurities react to calcium, it is become impurities, recycled calcium fluoride.
Okay. So regarding the zero liquid discharge, Mr. Nakano,
yes.
What is your opinion about the use of like newer technology like membrane distillation or forward osmosis or electrodialysis instead of high pressure RO? Because when we use high pressure RO, of course the energy requirement will be significantly higher as well.
Yes, it's depending on the volume of the water. So the evaporator's energy cost and energy consumption is extremely high compared with RO, about 10 times higher than RO. So we must reduce the water volume as much as possible. So in some circumstances, we adapt the UHPRO. So if the concentration of the TDS is around a few thousand milligram per liter, if we use the UHPRO, we can concentrate the wastewater to the
7 or 8% or more, around 10%. So the water volume before evaporator is become very low. So we can we have a cost merit by adapting the UHPRO or Discover.
Okay, so this is the combination between RO, HPRO, and evaporator.
Yes.
Okay, thank you, Mr. Nakano. Next questions. Okay, next questions is for Dr. Mimura. Dr. Mimura, how is the organizing for water reuse of risk analysis system?
Very difficult question. Thank you very much. It's a very difficult question. So now, in this point, I can answer your question to precisely, but if you have more times, please email the question of your opinion, and then I will answer you as possible as fast as soon as possible. Okay, so I'm sorry.
Okay, so this question will be emailed to Dr. Mimura. Thank you, Dr. Mimura. And another question for Dr. Mimura, the question from Professor Chandra. Why do we still need aerobic biofilter after DHS? Please explain why do we still need.
Okay, thank you very much. DHS is a very good system. It is about to alternate for air occupational search system, but DHS is very low electric power system, about 25% of occupational search, but DHS is just only tracking filter. That is, it does not have real liquid DHS system do not have clarifier and systems, but it's able some part it's able treated water. It's treated water. It's able to treat the water to little particle, and it's DHS HRT of DHS is very short than active search, and ammonia is a little the same. So because we need aerobic biofilter for pre-treatment to post-treatment of DHS. Okay, it's my answer. Okay, Mr. Chandra.
Okay, thank you, Dr. Mimura. And I have a questions regarding the comparison between the aerobic biofilter and the sand filtration.
Yes.
In aerobic biofilter, we need to introduce the air continuously. Am I right?
So, okay, answer please.
Okay, so in aerobic biofilter, we need to introduce air continuously to the tank. How that affect the water cost when it is compared to the sand filtration?
Your question is the cost, about the cost?
Yes. About the water cost.
But just sand filter treated speed and linear velocities and aerobic linear velocity of the aerobic biofilter speed is less than sand filter, but we cannot compare the cost between sand filter and aerobic aerobic biofilter. And its performance, its function is not the same. The sand filter can only remove only particle, but aerobic biofilter can remove particle, both particle and organic matter and ammonia. I cannot compare the both system and about cost.
Okay. Okay, thank you, Dr. Mimura. So next questions is for Mr. Nakano. After we get the fluoride back from the wastewater with high recovery ratio and purity in form of the calcium fluoride, can we use this as an industrial raw material, like in optical component manufacture?
Yes, we can use the pellet as an industrial raw materials. So in Japan, we actually sell the pellet, some fluoride chemical engineering maker for variable materials. If the purity is low, for example, 90%, we cannot sell the pellet for raw materials. And for example, the natural calcium fluoride we imported from China is around 96 or 97%. So the calcium fluoride which is produced by our product is same purity as a natural product.
Okay, thank you, thank you, Mr. Nakano. Next questions, if any. Okay, I think this is the last questions for this session. So for Mr. Nakano, if without evaporator, what is the profile of the concentrate? Can we do with that if it's not being evaporated?
If we don't have the evaporator, it is hard to achieve the ZLD. But we can reduce the water volume using by some method, pre-treatment method and RO system. So we can concentrate around 10% by TDS. But if we want to concentrate over the 10%, I have some method. We developed some method, but the evaporator is a very suitable method, I think.
Okay, so without the evaporator, we can have a very concentrated water, but we cannot achieve the ZLD, yeah?
Yes.
All right, okay. Okay, thank you. Do we still have another question? Committee?
Sorry, Helen, I think I would like to ask to Mr. Nakano.
Yes, please, Pak Chandra.
Yeah, Mr. Nakano-san. So,
yes.
If because of fluoride, it means that for the fluoride recovery, it's only for relatively pure one, because if coming from the other fluorides problem is coming from the fertilizers industries. So the fertilizer industry sometimes they produce they produce water content fluoride relatively high, but a lot of other impurities in the wastewater. So do you think the fluoride recovery can be used for the wastewater coming from the fertilizer industries?
Yes, but we have experiment. We have the experience about the semiconductor factory. So the semiconductor factory's HF is very clean.
Yes, yes, you are right. Yes.
If the impurities, so many impurities, it is hard to make grown crystals.
Mm.
So,
Yeah.
yes.
Yeah, I understand that. Okay, clearly. So that one is should be relatively clean. I mean, the impurities relatively small to recover the fluoride. Okay, thank you.
Thank you, Professor Chandra. So I think no more questions from the participant.
Yeah, I think so. Yeah.
Yeah, I think so. Yeah. So if there are no more questions, I would like to wrap up this event with a brief summary of the panel discussion sessions. Okay, so from the first and second session, we know that water reuse is extremely important, especially in our time with the shortage of clean water. And Dr. Mimura also have mentioned that in Japan, they have succeeded to treat the sewage wastewater and can get the clean water near drinking water quality. Yeah, that's very interesting. And now with the reduced price of the membrane, the capital expenditure of the membrane process will not be a problem, even for the relatively expensive reverse osmosis. But of course, the operation costs still need to be reduced, according to Professor Yamamoto. And for the country with a lot of small islands, of course, the renewable energy and the less chemical method will be important keys for the application of water reuse. Professor Yamamura also in the first session highlighted the use of bacillus bacteria to significantly reduce the organic fouling in the MBR. And interestingly, the reduction of organic fouling in MBR also extend to the organic fouling reductions on the next membrane process. So it's very important. To simplify the whole process, the whole water reuse process, Professor Wenton introduced us to the non-modular membrane, which is a relatively big membrane, but very simple to be operated. And lastly, Mr. Nakano have introduced us to the concept of zero liquid discharge, in which way we can get the most of the clean water and also we can get valuable crystals. So by tackling the inorganic scaling and also the silica scaling by adjusting the operation condition in RO, we can get at around 88% of water recovery. Okay, so the topic today, industrial water reuse, have been finished, and I would like, on behalf of the all committee, I would like to thank all the speakers for the time and for the knowledge you have shared to us in this webinar. Thank you, MC.
All right. Thank you very much, Mrs. Helen, and all the distinguished speakers. That was an interesting talk. I hope it can give us new insights and can be implemented to advance industry in Indonesia and Japan. Ladies and gentlemen, this is a kindly reminder. For those who have registered in this webinar session, please fill in the attendance list on the link provided in the chat room, both in Zoom and YouTube, for the purposes of sending certificates. Before closing the event, I will give you some important announcement regarding the main event of 2020 STKSR Symphosis virtual conference. 1. The deadline for abstract submission for the 2020 STKSR Symphosis is on the 31st of August 2020. 2. The 2020 STKSR Symphosis main event will be held virtually on the 16th to the 17th November 2020. 3. All information related to 2020 STKSR Symphosis activities can be seen on the website stkSR.che.itb.ac.id. Ladies and gentlemen, now we have come to the end of this event. On behalf of 2020 STKSR Symphosis Committee, I would like to express my utmost gratitude to all those who have supported this event and to all distinguished speakers and webinar participants for their kind attendance and active engagement in the STKSR webinar series pre-event. I would also like to apologize for any inconvenience throughout the event. Once again, thank you and see you at the next webinar series of 2020 STKSR Symphosis events. Bye-bye.
Thank you. Thank you.
Thank you.
Thank you.